All right, in this video, we're going to go through molecule polarity. This is a little bit more involved than just finding bond polarity. We're going to use bond polarity, and we're going to take it a step further to look at the overall polarity of a molecule. Okay, so the overall polarity depends on the sum of the individual bond polarities. And for this, you want to think in terms of vectors. So if you think back to physics when we looked at forces, or maybe in math class when you worked on vectors, or maybe this is the first time you've ever heard the word vectors before. If that's the case, don't worry, I will get you where you need to be. So in this first example, it says predict the overall polarity of CO2, which is carbon dioxide. First thing we're going to do is we are going to do our Lewis structure and find our bond polarities. So we have carbon, we have oxygen. Carbon, there are 4 electrons, and for oxygen, there's 6 electrons, and we have 2 oxygens, so we'll have 12 electrons total. 4 plus 12 is 16 electrons. Okay, carbon's in this molecule, so carbon's going to go in the middle. And then we go ahead and bond everything. So 2, 4 bonding. (16 minus 4 gives us 12 remaining electrons. Okay, and if we go to our table of electronegativity values, oxygen is more electronegative than carbon. So our electrons are going to go on oxygen. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so both oxygens are good now. However, carbon, not so much. Carbon needs 4 more electrons. So we're going to take these up here and we're going to make a double bond down here. So let me just go ahead and redraw that. Okay, so there is our molecule. The next thing we need to do is we need to go to our table of electronegativity values. Okay, so let's go back and take a look there. So oxygen is 3.44, carbon is 2.55. So for electronegativity, let's see, oxygen was 3.44, carbon was 2.55. So the difference between those is 0.89. And if we go back to that table, just below it, we have this scale, and we're in the range of 0.89 is in the range of a polar covalent bond. So this is a polar bond. Okay, since it's a polar bond, we're going to have dipoles. Okay, so on our molecule, since oxygen is more electronegative, our dipole is going to point towards the more electronegative molecule. So we have 0.89 pointing towards the oxygen here. And then we have another one on the other side. Okay, so this is kind of like a tug of war. Both sides are pulling with a force of 0.89. So since they're equal and opposite, they will cancel out. We will have 0. So this is going to be a nonpolar molecule. Notice it's symmetrical, so both sides are the same, and they're both pulling with the same amount of force. Okay, so let's just make a note here. So oxygen is more electronegative than carbon. But the vectors cancel. And when I say vector, I'm talking about those arrows that are pointing in the opposite direction. Let's take a look at another example. It says, predict the overall polarity of HCN. So for this one, we're going to approach it the exact same way. We're going to go a little bit quicker on this one. So we have hydrogen, we have carbon, we have nitrogen. Hydrogen has 1 electron, carbon has 4 electrons, and nitrogen has 5 valence electrons. Okay, so we end up with 10 valence electrons. Okay, carbon's in this molecule, so carbon's going to go in the middle. Doesn't matter which side the hydrogen and the nitrogen are. Remember, these are 3-dimensional shapes. We can flip it around. So we have 2, 4 bonding. Ten minus 4 is 6 remain. Okay, so if we go to our table of electronegativity values, nitrogen is more electronegative than carbon. Hydrogen already has 2 valence electrons, so the remaining 6 are going to go on nitrogen. 1, 2, 3, 4, 5, 6. So both hydrogen and nitrogen are happy, but carbon, not so much. So we're going to need to share some of these. So carbon needs 4 more, so let's share these and these. So we'll end up with a triple bond, just like that. Okay, so let's look at our electronegativity values next. Hydrogen, carbon, and nitrogen. So if we go back up, hydrogen is 2.10, carbon is 2.55, nitrogen is 3.04. So we're going to have to find the electronegativity between hydrogen and carbon, and then carbon and nitrogen, because those are the bonds that we're looking at. All right, so first let's do carbon, which we said was 2.55, and hydrogen, which is 2.10. So the difference between these is 0.45. Okay, and then we had nitrogen, which is 3.04, and carbon, which was 2.55. We subtract and we get 0.49. Okay, so if we go to our table and we go to the very bottom here, they fall in the range of a nonpolar bond, nonpolar covalent bond. So these are both nonpolar bonds. But let's take a look at something really quick. So since they're nonpolar, okay, we are going to have 2 vectors here. So we have one going from carbon to nitrogen. Okay, going from carbon to nitrogen. Nitrogen's more electronegative, 0.49. Okay, and then we also have from hydrogen to carbon. Carbon is more electronegative, so 0.45. So they'll point that direction. So in this case, the vectors are going to add. And one side is going to end up with more force than the other. They're not pulling in opposite directions, so we add these together. So in this case, it's a polar molecule. Okay, so again, the difference in electronegativity was small enough to be nonpolar bonds. However, when we add them together, since they're going in the same direction, they're both pointing the direction of nitrogen, it ends up being a polar molecule. Polar molecules are either not symmetrical, so we have 2 examples here. We have HCN, so we did this one earlier, looks like this. Okay, so without even throwing our vectors on there, you can see that the right side of this molecule has nitrogen, the left side has hydrogen. Totally not symmetrical, okay? Let's look at another one here. How about CH3Cl? Okay, so you just throw these on here really quick. Okay, so Without even throwing vectors on here, you can tell we've got 1, 2, 3 hydrogens, and then you have chlorine down here. Okay, so not symmetrical. They're not the same all the way around. Okay. The other thing that you might run into is a lone pair on the central atom. So the example here is NH3. So we have hydrogens all the way around. Okay, so you might want to think that it's nonpolar, but we have a lone pair on the nitrogen here. So with that lone pair, this becomes a polar molecule. So just maybe add this note here that lone pair exert a greater repulsion, causing its molecular shape to be unsymmetrical. And that's it. That's how you determine molecular polarity. To be completely honest with you, vectors might work for some of you, but the quick rules that we just went through, those are probably the easiest way to determine it. So good luck and have fun with these.